Right now, suspended invisibly in the atmosphere above the Pacific Ocean, there is an amount of water so large that the human brain genuinely struggles to process it as a real number. 20 trillion gallons. That is not a typo, and it is not an exaggeration used for dramatic effect. It is the kind of figure meteorologists actually calculate when a specific, well-understood weather phenomenon takes aim at the California coastline. And when it does, that water does not fall as an ordinary rainstorm. It arrives as a river, an actual river flowing through the sky, thousands of miles long and hundreds of miles wide, carrying more moisture in a single day than the Mississippi River carries at its mouth. Scientists call it an atmospheric river, and it is simultaneously the single most important water source California depends on to survive, and one of the most destructive natural phenomena the state regularly has to endure. Today, we're going to break down exactly what an atmospheric river actually is, how meteorologists can possibly calculate a number as staggering as 20 trillion gallons of water heading toward a single state, what happened the last time California absorbed a full sequence of these events back to back, and why this same phenomenon sits at the center of one of the most consequential climate questions facing the American West right now. Before we get into the details, if you live in California or anywhere along the West Coast, drop a comment and let us know what an atmospheric river season has actually looked like for you, whether that's welcome drought relief, filling up your local reservoir, or genuine flood damage to your home or your community, or, as has happened to no shortage of Californians over the past few winters, some difficult combination of both within the very same season. And if you want to understand the weather systems that are quietly reshaping how an entire region gets its water, go ahead and subscribe now, because atmospheric rivers are becoming an increasingly central part of the conversation around water security in the western United States, and this almost certainly will not be the last major system to make headlines this way. Let's start with the basic anatomy of what an atmospheric river actually is, because the name itself is doing a surprising amount of literal scientific work rather than functioning as some kind of catchy metaphor invented for headlines. An atmospheric river is a long, narrow corridor of highly concentrated water vapor flowing through the atmosphere, typically stretching thousands of miles across the open ocean and measuring hundreds of miles wide, moving with the broader patterns of wind, temperature, and pressure that shape a given storm system. Scientists consider them the largest transport mechanism of fresh water anywhere on the planet, larger in terms of total water volume moved than any physical river system on the surface of the Earth. The most famous variety affecting the west coast of the United States has earned its own nickname, the Pineapple Express, a specific atmospheric river pattern that hauls warm tropical moisture from the waters near Hawaii directly across the Pacific Ocean toward the coast of North America. When meteorologists talk about an atmospheric river taking aim at California, this is very often exactly the pattern they mean: a long ribbon of warm, saturated air stretching almost literally from the Hawaiian Islands to the California coastline, acting as a direct conveyor belt for tropical moisture into a temperate coastal state that would otherwise never see that kind of concentrated humidity. The sheer scale of water these systems can move is genuinely difficult to overstate, and understanding the specific numbers helps explain how a projection of 20 trillion gallons headed toward a single state stops them sounding like hyperbole and starts sounding like straightforward atmospheric physics. According to research on the subject, a single atmospheric river can move an average of roughly 10.5 trillion gallons of water per day, and the strongest of these systems are capable of transporting anywhere between 7 and 25 times as much water vapor as the average flow of the Mississippi River carries on the ground at its mouth in Louisiana. That comparison is worth sitting with for a moment, because the Mississippi is the largest river system in North America by drainage area, carrying the accumulated runoff of roughly 40% of the continental United States out into the Gulf of Mexico. A single strong atmospheric river, invisible to the naked eye and existing purely as concentrated moisture, floating several thousand feet above the ocean surface, can be moving more total water than that entire continental river system, all funneled into a band of sky that might be less than 300 miles wide. Once an atmospheric river makes landfall, the mechanism that turns all of that airborne moisture into actual rain or snow comes down to something meteorologists call orographic lift. As the moisture-laden air moving inland encounters California's coastal mountain ranges and, further inland, the towering wall of the Sierra Nevada, it has nowhere to go but up and over that terrain, sometimes climbing thousands of feet in elevation within just a few dozen miles of horizontal distance. As the air rises, it cools, and cooling air loses its capacity to hold water vapor, forcing that moisture to condense and fall as precipitation, often in extraordinarily concentrated bursts directly over the mountain slopes and the valleys and coastal communities positioned beneath them. This is precisely why California's most catastrophic flooding and its most valuable snowpack accumulation both tend to trace back to the exact same weather phenomenon, arriving through the exact same mechanism, sometimes within the same single storm event. Scientists at Scripps Institution of Oceanography developed a specific classification system for ranking the intensity of these storms, similar in spirit to how the Saffir-Simpson scale categorizes hurricanes, running from AR1, describing a weak system that is primarily beneficial, delivering needed rain and snow without significant hazard, all the way up to AR5, describing an exceptional hazardous event capable of producing widespread, dangerous flooding and destructive impacts. That scale matters because it captures something genuinely important about how meteorologists and emergency managers think about these systems. An atmospheric river is not inherently a disaster. It's a naturally occurring essential component of how California receives the majority of its annual water supply in the first place. Something in the range of 30 to 50% of the entire West Coast's total annual precipitation arrives specifically through atmospheric river events, meaning without them, California's reservoirs, its snowpack, and its overall water supply would simply not exist in anything resembling their current form. But that same research has also found that atmospheric rivers are responsible for roughly 80% of all flood damage recorded across the West Coast, which captures the genuine duality at the heart of this entire phenomenon. The same storm system responsible for filling a drought-stricken reservoir back up to healthy levels is also, statistically, the most likely single weather event to flood a neighborhood, trigger a landslide, or overwhelm a river's capacity to safely carry the water running off the surrounding hills. To understand what an actual sequence of these storms looks like when it hits California at full intensity, there's no better case study than the stretch of weeks spanning late December of 2022 through mid-January of 2023, a period that meteorologists and California residents alike still reference as one of the most extraordinary atmospheric river events in the state's modern history. Over the course of roughly 3 weeks, California was struck by 9 separate atmospheric rivers in a row, essentially back-to-back storm systems arriving with almost no meaningful recovery time in between them. By the time the sequence finally tapered off, the cumulative total came out to approximately 32 trillion gallons of water dumped across the state, an amount large enough that a University of California, Davis student studying atmospheric science, was able to calculate the figure independently using publicly available rainfall data and basic acreage math. A calculation that ended up circulating widely because it captured, in one almost unbelievable number, just how much water had actually fallen. That sequence of storms triggered more than 700 separate landslides across the state, contributed to at least 22 confirmed deaths, and produced an estimated $5 to $7 billion in total damage. California's governor at the time described the stacking of these atmospheric rivers as something the state had not experienced within living memory, specifically noting that even as the sequence approached its 8th of what would ultimately become 9 consecutive systems, residents needed to maintain their vigilance rather than assume the danger had passed simply because they were fatigued from weeks of continuous storm warnings. That fatigue factor is itself an underappreciated part of the danger these sequences pose. A single atmospheric river event, however intense, is a discrete, comprehensible hazard that a community can brace for and then recover from. 9 of them arriving back to back, with the ground already saturated and rivers already running high from the previous storm before the next one even makes landfall, represents a fundamentally different and more dangerous kind of cumulative risk. One where the danger compounds, specifically because the system providing relief between storms simply never arrives. That same sequence of storms did ultimately deliver the kind of drought relief California had been desperately waiting years for. Heading into that December, roughly 43% of the entire state had been classified under the 2 most severe drought categories tracked by the U. S. Drought Monitor, extreme and exceptional drought, following years of persistently dry conditions that had strained reservoirs, agricultural water allocations, and municipal supply systems across the state. By the time the 9 atmospheric rivers had finished moving through, the U.S. Drought Monitor showed that California no longer had any areas at all remaining in either of those 2 most severe drought categories, an almost complete reversal of the state's water crisis within the span of roughly a single month. Water storage across the state's 2 largest reservoirs increased by a combined 66% over that same window, and public water agencies estimated that roughly 27 million Californians would end up receiving significantly more water than they had been scheduled to receive just 1 month earlier before the storm sequence began. Snowpack across the Sierra Nevada, the mountain range responsible for storing a massive share of California's annual water supply in frozen form before it gradually melts and feeds reservoirs throughout the spring and summer, measured more than twice the historical average at several key monitoring stations by the time the sequence wound down. In California's agricultural heartland, the Central Valley, home to some of the most productive farmland anywhere in the country, the storms delivered exactly the kind of relief growers had been hoping for after years of water allocation cuts driven directly by the ongoing drought. That is the fundamental paradox sitting at the center of every atmospheric river story coming out of California, and it's worth stating plainly rather than glossing over, The same 3-week stretch of storms that killed 22 people, destroyed homes through landslides, and caused billions of dollars in damage, also single-handedly pulled the entire state out of its worst drought categories and refilled reservoirs that tens of millions of people depend on for their water supply. Neither side of that story cancels the other one out. Both are simultaneously completely true, and understanding that duality is essential to understanding why California's relationship with these storms is so fundamentally different from how most of the country thinks about severe weather. A hurricane making landfall in Florida is understood correctly as a pure disaster to be prepared for and endured. An atmospheric river making landfall in California is something closer to a gamble the entire state is forced to take every winter. A system capable of either saving the state's water supply for the coming year or devastating specific communities in its path, frequently doing some meaningful combination of both within the exact same event. It also helps to understand precisely why California, more than almost any other state in the country, ends up this dependent on a relatively small handful of storm events to define its entire water year. Unlike much of the eastern and central United States, where meaningful precipitation arrives fairly evenly distributed across the calendar in the form of frequent, moderate rain and thunderstorm systems throughout spring, summer, and fall, California's climate is defined by a pronounced Mediterranean pattern, meaning the overwhelming majority of the state's annual precipitation is compressed into a relatively narrow window, running from roughly November through March, with the summer months remaining almost entirely dry across most of the state in a typical year. That compressed wet season means California simply does not have the luxury of a long, gradual accumulation of moisture spread evenly across 12 months the way many other regions do. Instead, the entire state's water fortunes for an upcoming year, its reservoir levels, its snowpack, its agricultural water allocations, and its wildfire risk heading into the following summer and fall all end up hinging disproportionately on whatever happens to arrive during that narrow 4 or 5 month stretch. And within that already narrow window, research has consistently found that just a handful of the very strongest atmospheric river events, sometimes as few as 5 or 6 individual storms out of an entire winter, are responsible for delivering the majority of the state's total seasonal precipitation. That concentration is precisely why California's water managers watch every individual atmospheric river forecast with such intensity. Missing even 1 or 2 of the season's strongest systems, or having them arrive weaker than forecast, can be the difference between a comfortable water year and a slide back into serious drought conditions, regardless of how many smaller, more ordinary storms pass through in between. That same dynamic played out in reverse during California's punishing multi-year drought stretch that preceded the extraordinary 2022 into 2023 storm sequence. Water officials at the time repeatedly pointed to the simple absence of enough strong atmospheric river events as the single largest factor driving the crisis, rather than any broader, more diffuse decline in overall regional rainfall. The atmosphere over the Pacific during those drought years simply failed to organize the kind of long, sustained, high moisture corridors capable of delivering a truly substantial storm to the California coast, and without those specific systems, no amount of ordinary background precipitation was ever going to be enough to keep pace with the state's water demands. That is precisely why the arrival of 9 consecutive atmospheric rivers within a single 3-week window felt, to residents and water officials alike, less like an ordinary heavy winter, and more like an entire multi-year drought being erased within the span of a single month, because in terms of the specific mechanism actually responsible for filling California's reservoirs, that is essentially what happened. That duality has a well-documented, genuinely alarming historical precedent worth understanding in more detail, because it illustrates exactly how quickly an atmospheric river's beneficial water delivery can tip over into full-blown catastrophe when it overwhelms the infrastructure built to manage it. In February of 2017, a sequence of atmospheric rivers dropped enormous volumes of water on Northern California, and the inflow pouring into Lake Oroville, the state's second largest reservoir, exceeded the design capacity of the dam's main spillway. That spillway partially failed under the strain. Engineers then attempted to rely on the dam's emergency spillway, a backup structure that had never once been used in the nearly 50 years since the dam had originally been constructed. And that emergency spillway began eroding at a rate fast enough and severe enough that authorities made the decision to order the evacuation of 188,000 people living downstream out of legitimate concern that the dam's structural integrity could be compromised entirely. Repair costs from that single event ultimately ran past $1 billion. Subsequent atmospheric river research examining that specific 2017 event found that the warming climate had already measurably amplified the storm's total water content by somewhere between 11 and 15% compared to what an equivalent storm would have produced in a cooler climate baseline, a detail that connects directly to the broader climate science question hanging over every atmospheric river event California experiences going forward. More recently, in early February of 2024, Two atmospheric rivers struck California within a matter of days, producing record-breaking rainfall totals across multiple areas of the state and prompting states of emergency to be declared in several counties across Southern California specifically. That particular event brought hurricane-force wind gusts to San Francisco itself, along with wind gusts exceeding 100 miles per hour recorded up in the Sierra Nevada, extreme enough that a well-known storm chaser covering the event publicly described the flooding potential across parts of California as approaching biblical proportions. Widespread landslides occurred once again, multiple rivers overflowed their banks, and the storm system was ultimately linked to 9 confirmed deaths and roughly $3 billion in property damage. And the pattern has continued essentially every winter since, with atmospheric river sequences striking California again through the final days of December 2025 into the first days of January 2026, and another significant system tracking in late February of 2026, illustrating that these events are not some rare, once-in-a-decade anomaly, but rather a recurring, essentially annual feature of how California's water year unfolds, with the only real variable from year to year being how many of these systems arrive, how strong they get, and how much time passes between them. Now, let's get into the genuinely important scientific question hovering over all of this, because it's the piece of this story most directly relevant to understanding where California's relationship with atmospheric rivers is actually headed. Researchers studying the physics behind these storms have identified a fairly straightforward mechanism connecting a warming climate to more intense atmospheric river events. Warmer air is capable of holding significantly more water vapor than cooler air, a basic physical relationship that governs the entire water cycle. As the atmosphere over the Pacific Ocean continues warming, the air feeding into these long, narrow moisture corridors is able to carry more water vapor across the ocean before making landfall, which means that when a given atmospheric river does eventually strike California's coastline, it now arrives carrying a larger total volume of moisture than an equivalent storm system would have carried several decades ago under a cooler atmospheric baseline. That's precisely the mechanism researchers identified when they went back and re-examined the water content of the 2017 storm that nearly compromised the Oroville Dam, finding that warming had already boosted that specific event's total moisture by somewhere in that 11 to 15% range. It's worth being genuinely careful and precise about what current climate research does and does not yet confirm on this topic, because the science here is more nuanced than a simple one-directional story of everything getting steadily worse every single year. Long-term research tracking atmospheric river trends across California has found that while these storms are broadly expected to become both wetter and more intense over the course of the 21st century, that specific intensification trend has not yet been clearly and unambiguously observed in the historical data collected so far. Researchers studying this question have specifically noted that California's naturally dramatically variable climate, the state's well-known tendency to swing between severe drought years and extraordinarily wet years with very little in between, appears to be masking the underlying climate trend, meaning any gradual intensification signal currently developing may simply not become clearly visible in the observational record until considerably later in this century, potentially well after meaningful impacts from that intensification have already begun accumulating on the ground. What the same body of research has found more definitively, with considerably more confidence, is that California's mountain snowpack is measurably declining as a broader long-term trend, with more of the state's winter precipitation arriving as rain rather than snow, particularly at the lower and middle elevations of the Sierra Nevada that have historically captured a significant share of the state's frozen water reserves. That shift matters enormously for flood risk specifically, because rain runs off immediately, producing what hydrologists describe as flashier runoff, meaning streams and rivers rise more rapidly and unpredictably during a given storm, whereas snow accumulates gradually and melts gradually across an extended stretch of the following spring and summer, providing a much steadier, more manageable, and more genuinely useful water supply for reservoirs and downstream infrastructure to actually capture and store. That declining snowpack trend, layered directly on top of California's existing dependence on a relatively small handful of atmospheric river events each winter to supply the overwhelming majority of its annual water, is precisely why water managers and climate researchers across the state describe California's broader hydrology using the specific term climate whiplash, an increasingly common way of describing a climate that swings dramatically and rapidly between extremes rather than settling into any kind of stable, predictable middle ground. California's entire water year, whether it ends up classified as a genuine drought year or a genuine flood year, frequently comes down to whether just a handful of atmospheric river events happen to strike the state during any given winter, and whether those specific events happen to be well spaced out, allowing the ground and the rivers time to absorb the water safely, or whether they happen to stack up back to back the way they did during that extraordinary 3-week stretch spanning December 2022 into January 2023. That means the difference between a year remembered as devastating flooding and a year remembered as essential, life-sustaining drought relief can genuinely come down to nothing more than the specific timing and spacing of storm systems that, from a pure total precipitation standpoint, might otherwise look nearly identical on paper. This is exactly why research institutions like the Center for Western Weather and Water Extremes, based at the Scripps Institution of Oceanography in San Diego, have built out an entire dedicated research program specifically focused on atmospheric river forecasting and reconnaissance, including flying specialized research aircraft directly out into these storm systems while they're still developing over the open Pacific Ocean, gathering direct atmospheric measurements days before a given system ever makes landfall. That kind of advanced reconnaissance data feeds directly into the forecast models, responsible for generating exactly the kind of headline-grabbing total 20 trillion gallons of water projected to fall across an entire state that meteorologists use to communicate the sheer scale of an incoming event to the public well before the first raindrop actually falls. Getting that forecast right, both in terms of total precipitation and in terms of exactly where along the California coastline the heaviest moisture will ultimately come ashore, has enormous practical consequences. Reservoir operators need advance warning in order to make careful, deliberate decisions about how much water to strategically release ahead of an incoming atmospheric river, freeing up storage capacity to safely catch the coming surge without overtopping a dam spillway the way Oroville nearly did back in 2017, while simultaneously trying not to release so much water preemptively that they end up needlessly discarding water the state may desperately need later in the year if the storm ultimately underperforms the forecast. So what does all of this actually mean for the millions of people living across California and the broader West Coast, watching these enormous rainfall projections scroll across their phones each winter without necessarily understanding the full mechanism behind them? The practical takeaway from meteorologists and emergency management officials has remained remarkably consistent through every single one of these major events over the past several years. An atmospheric river forecast, particularly one projecting an AR4 or AR5 level event on the Scripps intensity scale, deserves to be taken exactly as seriously as a hurricane warning would be taken anywhere else in the country, even though it lacks the visually dramatic swirling satellite imagery and the assigned proper name that makes a hurricane instantly recognizable to the public. Residents in areas with any history of flooding or landslide risk, particularly anyone living below or downhill from land that has recently burned in a wildfire, since burn scars dramatically increase both flood and mudslide risk during subsequent heavy rain events by stripping away the vegetation that would otherwise help stabilize the soil, should have an evacuation plan and emergency supplies ready well before a forecast atmospheric river actually arrives, not after the first advisory has already been issued. Local officials across multiple counties have specifically urged residents ahead of major atmospheric river sequences to gather at least 2 weeks' worth of essential supplies, since a genuinely severe sequence, as California learned firsthand during that 9-storm stretch in the winter of 2022 and 2023, can render roads impassable, knock out power for extended stretches, and generally disrupt normal life across large sections of the state for considerably longer than a single, isolated storm ever would. There's also a broader, more structural conversation. This recurring pattern continues to push forward regarding California's water infrastructure more generally. Many of the state's largest dams and reservoirs, Oroville included, were engineered using rainfall and runoff data collected decades ago, under a set of assumptions about how quickly water would arrive, and how it would be distributed across a typical winter that increasingly no longer holds, given both the observed decline in snowpack and the theoretical still developing signal of more intense atmospheric river events layered on top of an already naturally volatile, whiplash-prone regional climate. Water officials across the state have been engaged in an ongoing, multi-decade effort to modernize forecasting systems, improve advanced reservoir management protocols, and, in some cases, physically upgrade spillway infrastructure, specifically in response to lessons learned from events like the 2017 Oroville crisis. But the scale of infrastructure involved means that kind of modernization inevitably unfolds over years and decades, rather than in response to any single storm season, regardless of how dramatic that particular season's headline-grabbing trillion-gallon totals happen to be. One of the more promising developments to come out of this ongoing modernization effort is a forecasting approach known as forecast-informed reservoir operations, a strategy that has been piloted and gradually expanded across several major California reservoirs in recent years, specifically to address the tension between flood safety and drought preparedness that atmospheric rivers create. Under older, more conservative reservoir management rules, dam operators were generally required to maintain a fixed amount of empty flood control space throughout large portions of the wet season, regardless of the actual forecast, a rule designed to guarantee enough capacity to safely absorb a major storm at any point, but one that also meant potentially valuable water. Sometimes had to be released and allowed to flow out to the ocean even in years when no major storm ever actually materialized to justify that lost capacity. By incorporating increasingly accurate reconnaissance-informed atmospheric river forecasts directly into reservoir release decisions, operators using this newer approach can hold back more water during stretches, when forecasters have high confidence no major system is imminent, only drawing down reservoir levels to create flood space specifically ahead of a genuinely significant, well-forecast atmospheric river event. Early results from reservoirs that have adopted this approach, including at Lake Mendocino in Northern California, have shown it can meaningfully increase the total water captured and stored across a given season without compromising flood safety, offering a genuine example of how better forecasting technology can help California navigate the fundamental tension at the heart of every atmospheric river season, squeezing more benefit and less risk out of the exact same storms. What makes the phrase 20 trillion gallons of water headed for California worth genuinely understanding, rather than simply scrolling past as an eye-catching headline, is that it represents something California has now experienced in one form or another essentially every single winter for years running, arriving through the exact same well-understood atmospheric mechanism and carrying the exact same fundamental duality every single time it happens. The water contained in that figure is neither purely a disaster nor purely a blessing. It is both simultaneously, and which side of that equation ends up defining a given winter for any specific California community depends enormously on factors that are only partially predictable. Even with the state-of-the-art forecasting and reconnaissance technology researchers currently have available, how many of these systems arrive within a given season, how much time passes between them, how saturated the ground already is by the time the next one makes landfall, and how much of that concentrated moisture happens to fall as gentle, valuable snow up in the Sierra Nevada versus flashy, dangerous rain running straight off already saturated hillsides. As California's snowpack continues its documented long-term decline, and as the broader question of atmospheric river intensification under a warming climate continues to develop in the scientific literature, that fundamental gamble, an entire state's water supply and an entire state's flood risk, both hinging on the same handful of storm systems each winter, is not going away anytime soon. If this breakdown helped you understand what's actually moving through the sky the next time you see a headline about trillions of gallons of water heading toward California, make sure to like the video, share your own experience with these storms in the comments, and subscribe so you don't miss the next update as this pattern, and the science tracking it, continues to develop through the rest of this decade and beyond.